Multicore processing is a relatively new method chipmakers are using to make computers and applications faster. This video will explore a bit about what this means and how you can take advantage of it with your applications. At any given time during your workday, you may have a variety of applications open at the same time. You may be looking up specs on the web, reviewing a spreadsheet, and debugging the software for a test system all at the same time with the same computer. Each of those applications has a unique process, and each process has its own thread as well as other shared memory resources. All of this is managed by the operating system, which schedules all the available tasks on the CPU. This allows the programs to play nice with one another within a shared resource. Multi-core systems work a little bit differently. With a multi-core processor, each application can be selfish and get its own space. This enables the individual applications to be more responsive. Some applications can even take advantage of the multiple cores to get things done faster. This is particularly noticeable with applications that need to process large amounts of data. As a software developer, you are probably most interested in how to optimize your specific application to take advantage of multi-core. There are two good techniques you can use to really optimize for multi-core. These are data parallelism and pipelining. To go into more detail, let's start with data parallelism. The easiest way to explain data parallelism is to show an example. So let's consider a problem in software where you have a large data set you need to operate on, like an array or matrix. If I operate on each element in the dataset using a single core, my algorithm may take this long to execute. That may be fine for some situations, but may be fairly long in other situations. If I had a quad-core system, I would have 3 other CPUs remaining that are just sitting there doing nothing. To give these processors something to do, I can break up my array into 4 equal parts and send them each a portion of the dataset. This breaking up of the dataset into smaller pieces and running a piece on each core is what data parallelism is all about. I essentially have 4 parallel processes going on at the same time, which makes my overall operation in this case run 4 times faster. When each operation is finished, I combine all of the results from each processor into a final result. In graphical programming languages such as LabVIEW, you can apply this method to the code itself. In a LabVIEW block diagram, you can split up a large dataset, perform the algorithm in parallel, and then combine the results. Keep in mind, this is only valid when the time to process a single algorithm is longer than the time to split up your dataset, analyze the parts, and recombine them at the end. If the time it takes to separate and then recombine your dataset is longer than the time it takes to actually do the analysis on a single core, then you should just stick with running it on a single core. Next, let's talk about another approach called pipelining. Pipelining is known as the assembly line approach because it works well for processes that require sequential execution, like the step-by-step processing of an image where each step relies on the previous step to execute. To illustrate how it works, let's take a look at an assembly line with 3 steps. The initial block comes into a first step. After this finishes, the data moves to the second step until it reaches a final step. If you think of each of the steps here as an individual processor and each box is a piece of data that needs to be processed, you will have a pretty good idea of how pipelining works. The benefit is that after the first processor finishes, it is ready for another box to process, which reduces the amount of time it takes to process all of the boxes. In other words, just like an assembly line, you don't need to wait for the data to move through all of the steps before starting on the next bit of data. To further understand how you would implement this on a multi-core system, let's assume we have a simple 4-step image processing algorithm that needs to be done in sequence. These steps cannot be done out of order because each is dependent on the one before it to execute. So what we will do is dedicate a CPU resource for each task. We can put step 1 on the first CPU, step 2 on the second, and so on. We then pass the data to the next step and repeat the process. At the beginning, it isn't very helpful, but after only 4 steps, we start to see some real benefits, and by the end we are moving data through all 4 steps at the same time. As with data parallelism, there are some things you need to be aware of with pipelining. First, the steps should be balanced. If step 2 was a lot longer than the other steps, then everything would have to wait for step 2, and our performance would be entirely based on how fast we can do step 2. Next, you need to figure out the optimal number of stages. If we only had 2 CPUs, then 4 stages may not have been optimal. Something else to keep in mind is that if you need to move large chunks of data between cores, that transfer may increase the total time for your process. As with data parallelism, pipelining can also be intuitively represented in a graphical programming language with products like NI LabVIEW. With pipelining, you can send your data through each step inside a for loop. Each step passes the data to the next step using shift registers. Because each step is isolated, it will be able to run on its own core. When the data has passed through all of the steps, you will have your final result. This concludes the video on Multicore and how you can use it for your applications. For more information on Multicore, go to ni.com/multicore.